Thanks for the introduction. Good afternoon, everyone. My name is Shaofeng Wu, and I come from the Chinese University of Hong Kong. And as the speaker today, I'm very glad to have this opportunity to introduce our recent work and experience on developing and deploying the next-gen solution for cloud network service offload at scale in Azure. The system is called SONiC-SmartSwitch, and it is a joint work between Microsoft and CHK. In this talk, I will discuss the motivating lessons behind this new solution and the innovations we make to achieve our design goals, as well as the performance numbers and the community impact. And without further ado, let's begin with the background. The scale of today's public clouds are growing fast. Microsoft has owned 65 regions and 200 plus data centers across the globe. The spending in cloud infrastructure is very huge, and the cloud providers are competing heavily on the market share. Hyperscale clouds today deliver infrastructure as a service, in which the cloud providers manage the underlying infrastructure and provide customers with virtualized computing resources. Cloud network services are one of the virtualized resources provided by Azure and have been highly important in terms of the performance and cost. Examples include stable firewalls, L4 load balancers, and so on. And what they have in common is that most of them need to keep a dictionary of flows and process packets based on the flow states. And we refer to this as being stateful or connection-oriented. So why do we care about cloud network services? The first reason is they have been the performance bottleneck. We have shown in our previous research that connection per second is very limited in major public clouds. The second reason is the cost. Using servers to host cloud network services are very expensive because it reduces the cost that can be sold to serve VMs. And these two challenges have motivated us to make relentless efforts to evolve the service solutions in Azure. So VIP is a software-based virtual switch and serves as the very first generation of unified service solution in Azure. And since then, we have been leveraging hardware, including FPGAs and programmable switches, to offload cloud network services because they are better at processing packets at a lower cost compared to host networking. They're still running in our data centers and serving VM to VM and VM to private link workloads. And in our latest generation of hardware solution, which is named Series, we disaggregate network services onto a novel DPU appliance that groups 6 AMD percentile DPU cards as a resource pool. And this allows us to deliver network-optimized VMs that require higher flow scale than that can be supported on single host and offload those very heavy middle boxes, such as stateful firewalls, which is a complementary to our FPGA-based solutions. And given the high performance numbers achieved, we ask a new question for the next generation of our solution. Do we learn any new lessons beyond pure performance by operating all these existing solutions in Azure? And the answer is yes. And I will introduce the 3 lessons that motivate us to innovate on some of the dimensions that have become the new bottleneck of our business growth. The biggest lesson we learned is the current software development model is preventing the fast iteration of cloud network services. Currently, we and other clouds take a development model that is not cloud-centric, and what features are available to us are determined by the hardware provider and their products. This is a compromise for better performance, but as a result, we need to carefully select the hardware platform that has all the features we need. Otherwise, we need to wait for the slow feature rollouts, and what's even worse is we are locked into a vendor. And there is no guarantee that the platform supports all the features currently required, will also support new features required in the future. The second lesson we learned is how we model our services will finally affect their performance. This is because when we use an approach that models a variety of flexible features, it becomes non-trivial or even impossible for the underlying hardware to optimize the performance for that big set of features. And we have tried using software-based VIP, which models cloud network services as layers and are proven to be too flexible to be accelerated with general programmable hardware. And currently, we are using vendor property SDK, which is well optimized on specific platforms, but does not offer us with the required feature and does not change the vendor-centric development paradigm. P4 is somewhere in between, but it is still too flexible and is usually used together with SDKs on different platforms. And therefore, we wish to redesign how we model our services and find a sweet point between feature variety and performance. The final lesson we learned is that the physical footprint of a solution matters a lot when we deploy it at large scale. This lesson mainly comes from the deployment experience of Series. Each Series appliance requires the new installation of 2 servers for cabling, cooling, and powering, and 2 switches for connectivity between the appliance and the data center core. This equipment makes our data center less efficient because none of them directly contributes to service processing logic, but does contribute to higher capex, power consumption, floor space occupancy, and human hours. And they also limit the deployment scale of series simply because we do not have enough room to place additional appliances in a pre-designed data center. And in fact, these limitations translate to over $100 million of revenue loss. The 3 lessons we have learned have motivated us to take several design goals beyond performance really seriously for the next generation of service offload solution in Azure. The preliminary requirement is to keep our solution vendor neutral. And in the server space, we need to model our services differently to reach a sweet point in the trade-off between feature variety and service performance. In the hardware space, we want to put our solution in the real physical world and reduce the space and the power footprint of the hardware. And finally, performance-stable packet processing is the bottom line under the above context. And to achieve these goals, we believe that fundamentally changing the development paradigm is necessary. The ideal model should be a top-down approach. Starts from firstly defining what features are most significant for our services and modeling our services in a new way. And then defining a unified interface according to these features. And finally, using service requirements to guide the design of the hardware. And under this guiding principle, we initiated the SONiC Dash project from 4 years ago. Dash is basically a set of vendor-neutral APIs that are compatible with the Switch abstraction interface and supports cloud network service scenarios. Around Dash, and with the operational lessons in mind, we redefine how we model our services and how to develop our services in collaboration with hardware providers and what hardware we want to deploy to offload our services. The final result is promising, as not only do we deliver state-of-the-art performance, but we also achieved all our design goals, including multi-sourcing and higher efficiency. And I will start with the first piece of our design by introducing how we model our services with Dash pipeline. So Dash pipeline is our new approach to model cloud network services. We decided to design it as a universal template of max action pipeline. And the reason is that we are able to find a set of basic building blocks that are used by all, or at least most of the network services. For example, flow table, ACL, and so on. And as long as we make sure that the Dash pipeline contains these modules, we are able to model all our services and make it specific for the hardware to optimize such a template. We list several examples to demonstrate this. So the first example is the connection tracking stage, which is fundamental to our services and should be included in the pipeline to be optimized. To program different services, what we do is just reusing the same pipeline, but configuring different packet transformation in the flow table. Another example is that we include a pipeline lookup stage to model multi-tenancy or multi-instance, which are required by many of our existing service scenarios, such as VM ENIs and load balancers. We have made many other design choices carefully to make sure that Dash pipeline is both generic and specific to cover most of the service scenarios in production. But due to time limit, I will skip the details. And ideally, we expect hardware providers should clearly understand the pipeline model so that they can implement and optimize it on their hardware and expose the Dash APIs for programming. This is similar to how Zhai works, but the problem is that previously we used documentation in English to describe the service behavior. And that means that even if the community have the consensus on features that should be modeled by Dash pipeline, there's no guarantee that this behavior is consistent across platforms. And therefore, this calls for process innovation, which is our second design of a community-driven development model. Our key idea to resolve this is to use P4 to model the behavior of cloud network services. And here we show an example of precisely and clearly modeling the expected behavior of connection tracking stage with P4. For example, we can specify without any ambiguity that flow key is a combination of EN and MAC, VNet ID, and 5 tuple. And how these fields are derived in earlier stages can also be modeled similarly with P4. And in addition to this, the behavior model also speeds up the entire development workflow. We are able to automatically generate Dash API headers by compiling the behavior model source code. And we are also able to bring forward procedures of writing test cases on the development timeline, because developers can run P4 sources on a reference software switch and can write test cases against it. The Dash APIs generated through the new development paradigm will be merged into Zhai and become part of the standard. For hardware providers, the good thing is when they implement Dash pipeline on their platforms, they know the expected service behavior clearly and can align their implementations with the behavior model and test cases. And since the Dash pipeline has been designed to be very specific from day one, So optimizing its performance are easier compared to optimizing other existing service models. And vendors can still keep their optimizations proprietary underneath the behavior model and the APIs. For cloud providers, their network services become vendor neutral, and they can choose the best of the cloud solution for their purpose, such as DPUs or different implementation of service and so on. But with the operational license in mind, we allocate a new SmartSwitch architecture for better deployability and scalability. I will then introduce this new hardware model as the last piece of our design. To quickly recap on series, its key bottleneck lies in the low efficiency and high footprint, and its positioning can also cause latency overhead due to traffic detouring. And to avoid these bottlenecks, we converge the switches and DPUs and build a SmartSwitch as an in-network resource pool to offload services. DPUs are directly connected to an NPU chip of the SmartSwitch via interconnects such as PCIe and backplane Ethernet. The Unibox SmartSwitch architecture offers several benefits in addition to the performance and disaggregation. So firstly, putting NPU and DPU in one box significantly reduces the rack space it takes to deploy and the power consumption it takes to operate a SmartSwitch. And second, SmartSwitch can be deployed and decommissioned with the same standard procedures as normal switches, reducing the operational complexity and cost compared to DPU appliances that require customized procedures. And finally, SmartSwitches can also shorten the data paths. Here, we show the offloaded data paths by SmartSwitch in our production deployments. The reachability from VM to SmartSwitch is achieved with the stateless encapsulation with a reserved VNI at the host network stack, which is VIP and Azure Boost for our case. We decide to let all the DPUs on a SmartSwitch to share one single VIP. The SmartSwitch NPU will be the front panel to forward the stateful traffic to corresponding backend DPUs at line rate based on the MAC address of the VM's version NIC. This ensures scalability and organic growth of the future deployments because the IP addresses that are routable at the infrastructure level are very limited. And the SmartSwitch DPUs are equipped with ASIC pipelines that supports high throughput and high number of concurrent connections, allowing us to disaggregate heavy use cases that cannot be well supported by a single host. There are also several other technical aspects of SmartSwitch design. Please check the links for details. Over the last 4 years, we have successfully operationalized the community-driven development model and deployed smart switches at a very large scale in Azure. This is for the first time the cloud and the hardware community works together towards a unified standard in the cloud network service domain. And we want to acknowledge the community efforts on developing the behavior model and supporting Dash on various platforms. And for Microsoft Azure, we have been collaborating with 10+ hardware providers to deploy Dash-capable smart switches. And the smart switch implemented by 2 of the hardware providers have been successfully shipped and deployed in production. For evaluation results, we show the lab and production performance of smart switches from one of the 2 vendors. This smart switch can be equipped with 8 field replaceable DPUs, serving 1.6 terabits per second of stateful traffic at most. For both throughput and CPS, we are able to linearly scale from the capacity of 1 backend DPU to 8 DPUs, delivering stellar performance. And in real production, smart switches are able to handle workloads with different patterns, including those heavy use cases, such as when the active connections of an NSDI reaching 2 million during peak hours. A reasonable amount of the capacity is still reserved for the organic growth of our business. In terms of footprint and efficiency, SmartSwitch has significantly higher throughput per watt, per rack unit, and per dollar compared to the DPU appliance due to the elimination of redundant equipment, which enables us to deploy the SmartSwitch at a very large scale in Azure. And we have gained valuable lessons from the deployments of Dash-capable smart switches. And these lessons include how to reduce the impact of upgrades and how to avoid congestions when 2 smart switches synchronize flow states, and what level of information is required for debugging offloading service. And please check out paper for details. Yeah, and finally, to summarize this work, we identify 3 deployment bottlenecks and propose SONiC Dash Smart Switch as a systematic solution. It is deployed at a very large scale in Azure and achieves state-of-the-art performance with high efficiency and community impact. Dash is fully open source on the SONiC Foundation, and we invite new members to join our community and contribute. And this is the end of my talk. Thanks for your attention, and I'm happy to take questions. Thank you.